Day three, the final day of graphing these rational functions. So this is a little bit more difficult topic, these problems. If I factor the numerator on this problem, I get negative x plus 2 times x plus 5, and then the denominator is x plus 6. So if I look at this, there are no removable discontinuities. I have one vertical asymptote at x equals negative 6, and the horizontal asymptote is going to be none. There's going to be no horizontal asymptote because the power on the top is bigger than the power on the bottom. But if I want to figure out what this graph actually looks like, the graph actually looks like whatever happens when I divide these two things out. So if I do synthetic division, with negative 6 because x plus 6 gives me a root at negative 6. And I have negative parentheses x squared plus 7x plus 10. I could rewrite that as negative 1, negative 7, negative 10 when I distribute everything. And then what I want to do is look at this. So what I have is a remainder of negative 4 after I use synthetic division. So what happens when I divide this out, if I remember back to last chapter, f of x is really equal to negative x minus 1 minus 4 over x plus 6. The oblique asymptote is negative x minus 1. So what that means is as the graph goes toward negative infinity and positive infinity, this is really going to look like this graph. If I zoomed out forever, it would just look like a line with slope negative 1 and y-intercept negative 1. That's not what the graph actually looks like as we zoom in on the area around negative 6 for x. But as we zoom out, and I'll show you on Desmos, as we zoom out, it really looks like negative x minus 1. So the x-intercepts of this graph are going to be where the numerator only equals 0. So that's at negative 2, 0, and negative 5, 0. And then the y-intercept is going to be at negative 10 sixths or negative 5 thirds. So I can put those points on the graph. So I have a point at negative 2, 0. I have a point at negative 5, 0. I have a x or a y-intercept at negative 5 thirds. So that looks something like this. And then what ends up happening is this graph basically looks like y equals negative x plus 1 in the long term. So this graph will look something like this. It's going to end up looking basically like a line with this as the asymptote as we go off toward the infinities. And so as I continue to graph this, it crosses these 2 points, then goes down forever. Since this x plus 6 has a 1 first power, it's not a bouncer, so it doesn't go to the same side. So it's going to end up going to different sides. And then the value looks like it's going to go back on this green dotted line path. So if I zoomed out really far, it would basically look like this green dotted line path. But as we get close to the blue vertical asymptote at x equals negative 6, things that are kind of weird happen. Problem 8, as we can see, it looks like the line y equals negative x minus 1 as we go out forever and ever and ever. It follows it very closely. But as we approach the vertical asymptote at negative 6, it behaves a little bit different. So the function crosses the x-axis at negative 2 and negative 5, goes down toward negative infinity for the function as x approaches negative 6 from the right, and as x approaches negative 6 from the left, it goes toward positive infinity, the function does, and then it appears to model this y equals negative x minus 1 very closely. Number 9, I'm going to factor this one. So the numerator is x minus 6 times x plus 1, and the denominator is x times x minus 4. So if I look at this, the denominator just has a GCF. Once again, there's no removable discontinuity in this problem. The horizontal asymptote is going to be at y equals 1. The reason I know that is I can divide the leading coefficients, 1 divided by 1, since the powers are the same. There are two vertical asymptotes, one at x equals 0 and one at x equals 4. The x-intercept in this problem, there are going to be two of them, one at 6, 0 and one at negative 1, 0. And then there's a y-intercept at, well, actually, there isn't a y-intercept. And the reason there isn't a y-intercept is if I substitute in 0 for x, notice that gives me a vertical asymptote. It makes the denominator 0. So I don't have a y-intercept. And that's why this problem is kind of interesting. So if I plot my vertical asymptotes at 0 and 4, my horizontal asymptote at y equals 1, and then I put my x-intercepts on the graph, excuse me, at x equals 6 and x equals negative 1, then I just have to basically plot my function. So as I'm plotting my function, the graph will look something like this. And the graph should look something like that as I go on. Now, one thing that's kind of important, and you'll have to learn this in honors pre-calculus, is if we take a look at the horizontal asymptote y equals 1, if you want to figure out where the function actually intersects the horizontal asymptote, I will take x squared minus 5x minus 6 over x squared minus 4x, set it equal to 1, and solve the equation. So I have x squared minus 5x minus 6 equals x squared minus 4x. If I solve this equation, I end up with x equals negative 6. So actually what happens is the graph is a little bit more complicated than what I showed. At x equals negative 6, this function actually intersects my horizontal asymptote, which means the graph goes above my horizontal asymptote and then comes back down. So that's a topic that you will see in honors pre-calculus, and I'm just kind of exposing it to you right now. If I look at this function, I see that there are uh, vertical asymptotes at 0 and 4. And then also we talked about how this function does cross the horizontal asymptote. So it crosses the horizontal asymptote of y equals 1 at negative 6, which we showed to be true. And so what ends up happening is this function goes above the horizontal asymptote, and then the function stays above the horizontal asymptote and then comes back and approaches it from the top side as we go toward x equals negative infinity. Problem 10, if I factor the numerator, I get x times x minus 1 times x plus 1 all over x minus 2. So once again, I have no removable discontinuities on this problem. My vertical asymptote is going to be at x equals 2. My horizontal asymptote, there's going to be no horizontal asymptote. My x-intercepts are going to be at x equals 0, 1, and negative 1. I should write those as points. So 0, 0, 1, 0, and negative 1, 0. My y-intercept is going to be, if I substitute 0 in, I once again don't have one because, or I'm sorry, I do have one. It is at 0, 0 because I already knew that. So now I'm going to start plotting points on the graph. 0, 0, 1, 0, negative 1, 0, and then I have a vertical asymptote at x equals 2, and I don't have a horizontal asymptote. Now, if I want to understand what's happening with these horizontal or these non-horizontal asymptotes, these slanted asymptotes or oblique asymptotes, once again, what I'm going to do is I'm going to take this function and divide it by x minus 2. So I'm going to do some synthetic division. The numerator is x cubed minus x. So that's 1, 0, negative 1, 0 for my synthetic division. So I end up with a 2 here. 2 times 2 is 4. 3 times 2 is 6. So my remainder is 6. If I wanted to rewrite this function, I could rewrite it as f of x equals x squared plus 2x plus 3 plus 6 over x minus 2. So what that means is my graph will actually look a whole lot like x squared plus 2x plus 3. So it's going to look like this parabola basically, except around my vertical asymptote. So what's going to happen with the function is I'm going to have a function that kind of looks like a parabola. So the parabola would have negative b over 2a as its vertex. So that's negative 2 over 2, which is negative 1. Then if I substitute that back into the parabola, I get 2. So negative 1 comma 2 is basically what the parabola's vertex would look like: over 1 up 1, over 2 up 4, over 3 up 9, and so on. So this parabola is basically what I'm modeling my curve after until I get close to this vertical asymptote. So as I get close to this vertical asymptote, things start to happen. So it does a little dance around here, goes down, and then it will start to come back up over there. Um, most of these problems that are on this page are not going to be tested on, but it's really kind of important to understand what's happening and why things happen. If I look at this function, x cubed minus x over x minus 2, the function does a lot of dipty-doing around negative 1, 0, and 1 for the x values. And then there's that asymptote, the vertical asymptote at x equals 2. But if I look at the graph that it kind of models as it goes off to infinity, notice that on both the left and the right side, it starts to look like that parabola really, really close. It's just as we are going off toward this asymptote, it diverges from that pretty significantly. So I'm going to uh, make the x-axis pretty wide here. And as you can see, this function looks like this parabola, except around the asymptote. What is the graph of this going to look like? And what about this one? A couple things to note before we show the graph on Desmos. Notice that there's no x-intercepts because the numerator will never be 0. There's no y-intercepts because the denominator will never be 0. And the function, so f of x, is always greater than 0 because no matter what you plug in for x, it's always going to be, the denominator is always going to be positive and the numerator is always 5. And then think about how that applies to this one as you move along and we show both graphs on Desmos. Notice that 5 over x squared plus 1, this kind of grows and then it shrinks back again. So the horizontal asymptote is clearly going to be at 0. And then it makes sense that there is no asymptote for the vertical asymptote because the denominator will never equal 0. And this will always be positive. So I have no x-intercepts. So the graph should look something like this. And then when I have 4x plus 5, the only difference is I do have an x-intercept. It's going to shift the graph over a little bit as well. My high water mark will not be at x equals 0. But there is an x-intercept. And then as I approach negative infinity, the graph is going to go back toward y equals 0.